Okay, prove the Babylonian sequence starting from the value 1 converges to the number which squares to 2. Okay, so this is going to use the monotone convergence theorem. This is going to use induction. This is going to use the arithmetic geometric mean inequality. It's going to use a lot of things. Okay, so first, what is the Babylonian sequence? So you have to remember what it is. Babylonian sequence starts, I don't know, maybe x1 equals 1. I think your book says x0 equals 1. Yeah. This is page 89 of your book. But I don't know, I like x1 equals 1. We'll start it there. And recursively, the xn is equal to the average of the previous one, xn minus 1, plus 2 divided by the previous one. Okay, so the new one is determined by the previous one. Okay, so first, we need to show that this converges. Need to show this converges. To do that, we will use the monotone convergence theorem later. So I'll put later. First, we'll just show that if it converges, then it converges to this root 2. First, if it converges, so xn goes to some number x, then x is equal to the square root of 2. And here's the proof of this little part. So we just invented a name for the limit of this sequence of x sub n's. So if x is equal to the limit of the x sub n's, well then we know that the x sub n is determined by this formula, so it's the limit of this thing just plugging in. And now we use limit laws. Limit laws. We're assuming that the sequence converges, so this sequence also converges, which is just shifted by 1. So the limit laws give us that this limit is equal to 1/2 times the limit of the xn minus 1s plus 2 divided by the limit of the xn minus 1s. But those are just x. We already gave a name to that limit. We named that limit x. Now we want to show that x is square root of 2, so now we have, we have x equals, x equals, x equals. Okay, and now we have an equation. So let's multiply both sides by x to clear the denominators. And I guess let's multiply both sides by 2 as well. So, or I don't know, maybe first I'll just plug in this over 2. I don't know what I'm supposed to do here, but now let's clear denominators, and I get x squared equals x squared over 2 plus 1. So I just multiplied everything by x. Okay. Now I can subtract this, and now I can, I have 1 of something minus 1/2 of something. That gives me just 1/2 of that thing. Now I multiply by 2. There's probably an easier way to do this, but I see that x squared is equal to 2, as desired. So we can call x by a new symbol called squiggly line 2. Okay, it is some real number, some Cauchy sequence that we didn't have before in the rational numbers. But anyway, okay, so this was the end of this mini proof here. Okay, so now I've shown that if the sequence converges to some number, that number must be the square root of 2. Okay, now we need to show the sequence converges. So now, why does the sequence converge? The monotone convergence theorem says if xn, if this sequence is bounded and monotone, in particular if it's monotone decreasing, then it converges. Okay, so now we just need to show, so we need to show bounded and decreasing. And then we would be done if we can prove two things. Okay, so let's first show that it's, let's experiment. So x sub 1 is 1. X sub 2 is 1/2 of x sub 1 plus 2 over x sub 1, which is 1/2 of 1 plus 2, which is 3/2. Okay. X3 is 1/2 of 3/2 plus 2 over 3/2, which is 1/2 of something. Oh, okay, let's put common, so 4/3. Let's do a common denominator of 9/6 plus 4/3 becomes 8/6 equals 1/2 equals, what is that, 17/6, which is 17/12. Okay, now it might not be clear, but we start at 1, and then we go up to 3/2, and then we actually go down to 17/12. So what's happening is that, here was my proof before of decreasing, but what's happening is that we start at 1, and then we go not to 2, but to 3/2, which is, where's 3/2? Like maybe here. And then we're going to just start marching down. So the claim is it's going to start decreasing. In other words, after the first number, when we jump up to 3/2, we're always going to go down from here on out. Okay? So we need to prove that. And you'd probably need to do a few more experiments to convince yourself that it is going to start decreasing. But it will, and we'll try to prove it now. And by experiments, I mean you'd have to calculate x4, x5, x6, and then you'd notice that it's always getting smaller, going towards square root of 2, wherever that is. Okay. Now, how do we prove that it's decreasing? Well, we're going to do it by induction. So, first of all, we're only going to prove that it's decreasing for the index 2 and onward, because it actually increases at first, and then it decreases. But that's enough, because we can just throw away the first term of our sequence, and the remaining thing will converge, and then by monotone convergence theorem. And so we'll be okay. But let's show it's decreasing. So we're going to use induction. After decreasing after the first element. In other words, the sequence starting at x sub 2, going x sub 2, x sub 3, x sub 4 is decreasing. So base case is that we checked that from x2 to x3, it is decreasing. Well, let's check that. Is x3 really smaller than x2, so that's decreasing? Well, x3 was 17/12, and x2 was 3/2. So let's cross multiply. 2 times 17 is 34, and this is 36, and yes. So this inequality is true if and only if this inequality is true. And so this one is obviously true, therefore this one is also true. And therefore this one is true. So here we're done with the base case. Okay. Now induction says assume that we have shown that we know that some, let's say, xn is less than or equal to n minus 1. Okay, so that we're decreasing, like the next sequence is smaller than the previous. So if we assume that if we can show this implies that the next one, xn plus 1, is less than or xn, then we have proved xn starting from n2, 3, 4, 5, etc. is decreasing, is monotone decreasing. Decreasing. Okay, so we need to assume this and prove this. Okay, so let's look at this one. Xn plus 1 less than or equal to xn. This is what we need to prove. And we're assuming this is true. But look, we can rewrite this. This inequality is true if and only if. What's the definition of xn plus 1? And what is the definition of xn? Well, it's a recursively defined xn minus 1 plus 2 over xn minus 1. And so look at this. We know stuff about xn and xn minus 1. We assume that we know this. So I wonder if we can, okay, let me get rid of See, I was quizzing myself. This is the second time I've done this proof. So if we can somehow blah, 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 if and only if, and we see that there's some true statement, some true inequality, then we're done, because we can go back up with the if and only ifs and get the one that we wanted, which was this one. Okay, so that's the strategy. So now there's really no thinking. We just want to manipulate this and have in mind that we know this is true. Okay, because at some point this should hopefully appear somewhere. So let's first of all, let's just get rid of these 2's. Okay, so this inequality is true if and only if I multiply everything by 2. Okay, and now let's multiply everything by xn to clear this denominator, and multiply everything by xn minus 1 to clear that denominator. So first let's multiply by xn, so I don't make any mistakes. Xn squared plus 2 less than or equal to xn minus 1, xn. For some reason I want to just switch the order. And then 2xn over xn minus 1. Okay, I just multiplied by this denominator to clear it. Now I'll multiply by this denominator to clear it. This inequality here is true if and only if multiply by xn minus 1. Oops, look at, I need to multiply this one by xn minus 1. See, I almost made a mistake. Okay, and now I should really just, these look similar and these look similar, so I should just put them together. I don't know if that's going to do anything useful or not. So I subtracted this one from both sides, and I subtracted this one from both sides. Okay, this inequality is true if and only if. Now let's factor out this, and we have remaining that less than or equal to, and let's factor out a 2. Okay. And now let's look at this. Here we know something about this, and we know something about this. Is it positive or negative? Well, xn is smaller than xn minus 1. So xn minus 1 minus xn would be greater than or equal to 0. And so xn is smaller than xn minus 1. So these are negative. So this is negative, negative. Okay, so if I divide through by both sides by that, I need to switch the inequality. Okay, and now I've got this. Now, this is interesting. If we can show that xn is greater than or equal to the square root of 2, and xn minus 1 is greater than or equal to the square root of 2, then this is true, right? Then xn times xn minus 1 is greater than or equal to the square root of 2 times the square root of 2, which is 2, which means that this thing is greater than or equal to 2, which is exactly this statement. And we're done. If we can show that. If we can show that this is true. Because then we know that this is true, and we follow up all the if and only ifs, and we get that this is true, which is what we are trying to prove for our induction step. Okay, so now, how do we show this? Well, this is where we use the arithmetic geometric mean. Arithmetic geometric mean. So remember that this is something about the arithmetic mean, and then it goes one way or the other way with this. Okay, so now we have to remember which way it goes. So if I take a is equal to 9 and b is equal to 16, or wait. A is equal to, how did I do this last time? Let's see, 3 plus 4, and then if I do 3 times 4, that's 12. What if I do something that gives, see, I don't know if this is true or not, 7 halves. I'm just trying to remember which way it goes. So I'm experimenting. And let's square both sides, 49 over 4 and 12. And then if I multiply by 4, I see 49 and a 48. Okay, so it must go this way. So I've determined that it goes this way, not that way. Okay, so that was sort of scratch work. Let's get rid of that. So this is an inequality, sort of like the triangle inequality, where you just need to use it at a bunch of moments. Here's the triangle inequality again. And we're not going to use the triangle inequality here, but we are going to use this one because we want to show that this is true. And so let's try to show it. So remember that xn is defined to be this. But this looks like this side. So I know that that's greater than or equal to, and now I just plug in for a and b, the square root of, and now this is a, this is b. No, times. These cancel. Square root of 2. So you see that we have this is bigger than the square root of 2. And similarly, so is this one. And so that means that this is true, which was our last inequality. And then we can follow it all the way back up to this one, which completes our proof by induction and shows that we're decreasing. Now also, why this is important too, is that, okay, so first this shows star is true, hence our sequence is decreasing by the induction proof above. Now what's star? Star. Okay. Great. Now, this also shows that our sequence is bounded below by root 2. In other words, root 2 is smaller than everything. Root 2 is smaller than all of our sequence elements. You see that? Root 2 is smaller than all of our sequence elements. I'm reading the inequality this way, which is why I said smaller than, because I'm saying root 2 smaller than xn. I mean, more typically you would just reorder this. And now this really is a smaller than or equal to symbol, or less than or equal to, /LEQ in LaTeX. Okay, so that shows it's bounded. And that means by monotone convergence theorem, xn converges. And we are done. Because we already showed that if it converges, its limit is the square root of 2. This is a great problem. You can see it took quite some time for me to prove it. Your book uses calculus, which I think is sort of cheating. Because we're trying to develop proofs, and we don't even really, I don't know. Well, maybe it's not cheating. We didn't really develop everything from the foundations, so. But this is a different way to prove it. And this is one of your problems. It's a problem that is, worth your time. And by really learning this problem, you can learn about recursive sequences. You can learn about convergence and finding the actual limit using the recursive formula and the limit laws. But then you're also using the monotone convergence theorem, which is one of the most important theorems we're learning in this class. And to do it, you have to show that it's bounded and decreasing, which means you needed to use a proof by induction. And that's tricky. So this is a great way to sort of understand what induction proofs do and how they work. Finally, you're using one of these really important inequalities, the arithmetic geometric mean inequality. To me, inequalities are quite often difficult to remember, so I just experiment with them a little bit first. And yeah, and remember, we've seen the proof of this. This is one of your other problems. It involved doing a minus b squared and a plus b squared. Okay.